Another video of showing some of the capabilities of TopSPICE. They just implemented a FRA, which is a frequency response analysis on TopSPICE, which means that you're able to extract AC small signal characteristics or basically transfer functions or Bode plots using a switching model instead of using a average model. Okay, so let's take a look. First of all, this would be a switching model. An average model, for those that are familiar with some of the videos that I have made in the past, this is a average model. And where I use a current source, basically a voltage control current source to model the PWM, the MOSFET, the transformer, and the diode. Okay, so if you have a flyback, you would do that. You would use this model. You can also use this model if you have a buck, which is what we're actually modeling. So then you have your divider network, your integrator, and then, like I said, this is a real simple model. Now, this is a model that was taught to me by my mentor, Jack Alexander. There are some other models that you can use, average models. You can use the Vachi model. There's also a model by Dr. Ray Ridley, and there's another model from Ben Yakov, and I believe there's some models also available from Kopek, which is the University of Colorado. So they also have some models, but the simplest one that I've seen is Jack's, so this is the one that I use. Okay, so this is very good when you're going to extract an AC loop analysis. And you can also extract the plant, meaning your output filter, and you can also extract the response of your integrator or your FRA. Okay, and typically you can only extract that using a average model, but in this case there's a new feature. Go to the right schematic. Okay, a new feature that you can use a switching model basically, and you can break the feedback loop, and you can insert a stimulus, and that stimulus basically feeds a wiggle into the system, a low disturbance, and that disturbance then gets treated or amplified by the pulse width modulator, and then it goes out. This is a switch which is emulating a MOSFET, and then this is your buck, and for the output that gets connected back into here. So basically it sends a signal out, and then the signal returns, and the FRA measures the amplitude difference between the out node and the in node and plots the gain and the phase. Okay, which is a very powerful tool. Now, in reality, and on the bench, we do a very similar function or operation. We actually break a loop and we insert a resistor, and we use, there's a couple of FRAs. There is the Venable, which was the original FRA that came out in the market, and then there's the Ray Ridley. Let me backtrack. The Venable, they run about 15 to 30,000. That's the FRA, and then there's the Ray Ridley. They run about 15. Then there's the Bode 100 that runs about 5 to 10, and then there's some other ones in the market. I use the Clever Scope that runs about 1500 to 2000, and then there's other units. I believe Analog Art and the Picoscope can also do a multiplot. Okay, so anyway, I went off on a little tangent, but going back to this, basically with the software that they added, you can do a loop analysis. So I'm going to show you how to do that. So before you do that, you want to do a run. You want to see how long does it take to come in steady state, because you use that information to start the FRA. So let's run a quick simulation. In this case, I'm going to disable the frequency response, and I'll let it run for 5 milliseconds. Okay, and I should be plotting out 1 and V2. This is the first. What we're interested is in getting the steady time. And it's how long does it take for this capacitor, your output filter, to charge from 0 all the way to 5 volts and then remain steady state. And I'll explain the reason why that information is important. Okay, so if you notice, I have a wiggle, and the reason I have a wiggle there is because I have this signal being fed into it. Okay, so let me go ahead and turn it off again. But just for here, this would tell me, even though it has the wiggle, the output filter went from 0 to 5 in about 371 microseconds. So after 371, it has already reached one steady state. So in this case, I'm going to go ahead and choose 1 millisecond as the time for the FRA to start outputting a stimulus signal. Okay, so let me just go ahead and set this to 0 just to show that since I turned off the FRA, that sinusoidal should go away. And that should be close enough. Okay, again, it's about 344, 371. Okay, and if we say, we're going to go ahead and say that at 1 millisecond we reach steady state. Okay, actually steady state is here, but we'll go ahead and choose this just to make sure we have enough margin. Okay, so remember that 1 milliseconds for steady state. Okay, so now we'll go ahead and turn the sine wave back on because we're going to use that. Okay, and let me explain one more thing. And we also have to specify 2, actually 1, but just so the simulator will run, we'll set the amplitude in this case to 300 millivolts peak, and we'll say that it's 1 kilohertz. And this is just to get it to start to run. You need a number defined there for frequency, so we'll set it to 1. But in actuality, we're going to sweep the frequency of the VFRA, and we'll do that here. Okay, so we'll go to Transient, and then we'll go ahead and put enable and then setup. Okay, so this is where you set up your frequency response analysis. So your stimulus, in other words, is going to be a voltage source, and it has to be a sine model. In this case, I named it FRA. So you type that in, FRA. You can also, if it's V1, you can put V1. You can pick whatever name, but as long as you reference it, that's the most important. Okay, so there's three types of frequency stepping. You can do linear, decade, and table. Under linear, when you turn that on, then these light up and it tells you, or you can input actually the start frequency and the stop frequency. So you can go from 300 to 100K, but then you have to pick what is the linear steps that you want it to step at. Okay. Now I prefer the decade, so it's 300, same 100 kilohertz, and in this case I'll pick 7 points per decade. Now there is a third, and this is one of the features that they just implemented. I had asked TopSPICE or Pencil Development if they could implement this, and they finally did, and it works great. But on this one, it's a table, and basically this table is defining the frequency and the amplitude that you want it to step. So in this case, the first is 100 hertz, and I want 1 volt, and then I want 300 at 1 volt, and then 400 at 1 volt, and so forth. So basically what I'm doing in this case, as the frequency goes up, the voltage actually decreases, and then it maintains it at 100 millivolts. So this is a very powerful feature, and I'll show you why this is powerful. Okay, so before I show that, I'm going to go ahead and show this decade plot. Okay, so we'll do that. Now remember when I was talking about the steady state time, remember it came into steady state in about 370 microseconds, but we went ahead and we said we're going to leave it at 1 millisecond. That way we have enough margin, and it'll start the stimulus after it's reached 1 millisecond. Okay, and then the time step ceiling, you can set this from 100 to 300 nanoseconds. If you make this lower than 300 nanoseconds, then the simulation gets longer. It takes longer for it to simulate. So it won't take as long. I'm setting it to 300 nanoseconds. And then the maximum time run is this. In other words, let's see if I can explain that. That is the maximum time. See if I can get the calculator out. Okay, so this is calculated by the lowest frequency that you're going to start. So the period for 300 is the reciprocal of that, and that's 3.33 milliseconds. And let's say this is 3.3 milliseconds for one cycle. So if I want 2 cycles, then it would be times 2. But if I want 3 cycles, it'd be 10 milliseconds. Okay, so by putting this at 10 milliseconds, what it's going to do is it's going to run the 300 hertz, and it's going to run it long enough where it will fit 3 of the 300 cycles. Okay, so that's what you want to set that at. And then this is the number of periods. In other words, on the first run we want 3 cycles, but then after that we want 6 cycles. So this is what this is doing. So the longer the cycles is, the better your FTT is going to be. Okay, so typically anywhere from 2 to 6, you'll have to play with this to see what is the best result that you can get. Okay, so then the final is, what is your measuring points? Where are you going to take the measurements? So in this case, I'm going to take a measurement from out to in. So then I would type that in here as out to in. So now I'm set up. Don't have to do anything else. Okay, and hit run. And it starts running. Okay, it's done. Okay, so here's the plot. So typically I don't like to see the plots on 2 planes. I like to see them in the same. So let's go ahead and we'll go to trace and smooth, and I'll go to plane 2. I'll cut, go back to plane 1, paste. Now they're same color, so I'll go to options, highlight the face FRA, and then make that a light red. Okay, that looks good. So now we'll change this to low frequency since we started at 300, and be a little bit consistent with the Ridley plot. We'll set it there. Okay, so before I copy, I'll go ahead and say that crossover is approximately here, the face here. So I believe the crossover is about 7.29 kilohertz, and the phase about 61 degrees. I'll put 31, it should be 61. Okay, so I'll go ahead and copy that, and then let's examine this and see if I can zoom in first a little bit. Okay, so this is the Bodhi plot from the Ridley TopSPICE, and if you look here, the green solid one is the gain, and this dotted slash is the phase. So here's the 0, and this is 20. So this is 10 kilohertz, 20 kilohertz. So if I can move this down a little bit. Okay, it's 10 kilohertz, so it has a crossover at 20. Okay, and the simulation that I have is 7. Okay, so now there's another thing that I want you to notice is if you look at the TopSPICE, boy, I gotta upgrade to a faster computer, that's for sure. Maybe it's because I have so much open. Close all. Close all. Okay, maybe it'll run a little faster. Okay, so here's another observation that I want to show. Yeah, it's running faster. Okay, if you notice, this line is basically straight, which is what you want. Okay, now take a look at the one that I just did. And if you notice, it starts out straight, but then here at the crossover, and the crossover of this was measured to be 7.2 kilohertz. Notice that it has this little deflection, and then it kind of straightens out again. Okay, and then you also notice here that this is a little bit different. Now, I want to explain this. Okay, the simulation that I did, the stimulus that I used was constant. It was basically 300 volts throughout the entire frequency range. So basically, it was the stimulus was 300 millivolts all the way through. And as you get closer to the crossover frequency, the voltage, being that it's a gain of 0 means that the voltage at V out and Vn are going to be equal. Okay, and so what does that mean? Well, it means that sometimes with a large stimulus going in, it has a tendency of clipping or exceeding the small signal values. In other words, you start to get distortion. Okay, and distortion is bad. So that's what we're getting right here. During this, there's distortion. Okay, and you can probably see this a little bit better if you do this. If we go to the transient, okay, so this is the out node, and then this is the in node. And if you notice this, you can barely see a signal, and then you see a signal there. Okay, so what I want to do is I want to go ahead and compare. I'm going to go ahead and compare these signals. Okay, the beginning, the middle, and the last ones. Okay, so this is the lowest. Okay, so first of all, this is telling me that I have a good signal, and I believe this is peak to peak is going to be 600 millivolts. Okay, but there's supposed to be a wiggle here, and you hardly see any wiggle here. Okay, so you would have to expand this to see an AC. So let's go see if we can expand that and see, do we see any wiggle? It's hard to say. So in this case, at this low frequency, I should be pumping a much bigger signal. This is only, it's 300 volt peak or 600 peak to peak. So I should maybe double or maybe even triple this. Okay, so that's the first point that I want to do. show. Basically, low frequency, I need to pump more signal. Then let's go ahead and eliminate the 300. Let's look at the middle frequency. Okay, so now let's look at that. Okay, so now you notice this is a crossover and they're supposed to be kind of equal. And if you notice, the scale is relatively the same. And if you look at this one, this looks more sinusoidal, although there's a little bit of distortion here. But then if you compare this output, if you notice, this is kind of straight. And then you see that you have a little bit of jackiness. It kind of looks like a sine wave, but it looks more like a sawtooth. So this is already distorted. So meaning that I have too much signal here. And then you can also say the same thing here, that I have too much signal too. So basically what I get from this is at the low frequencies I want to pump a higher amplitude, and then as I go up in frequencies I want to back down on the signal. Okay, so how do I do that? So that's one of the great features that was implemented recently, and that was by making this signal a variable amplitude. So what we can do is, in this case, we'll go to setup. So now we click table, and we can go to the edit. And if you're not sure if you can see this, but the first line is 100 Hertz. I'm going to go ahead and take that off just to be consistent. We're going to say 100 Hertz. And remember, I started at 0.3 or 300 millivolts. I'm going to go ahead and set that to 1 volt. Okay. Then 400, 1 volt. 600 Hertz, half a volt. 800, half a volt. And then right here at 2 kilohertz, then I reduced it to 0.1. And then I reduced all of that all the way up to 100 kilohertz. So from 2 kilohertz to 100 kilohertz, I made it 0.1. That way the signal would not distort as much. Okay, so now that I have that, let's see what kind of signal are we going to get. Okay, so here's the simulation. Go ahead and go into the log, make that log, and then we're going to go ahead and copy actually this one, cut, paste. Okay, and let's go ahead and cut this out. So we'll make it 300 to 100K. Set that to 100, 120 dB. Okay, so now immediately I see this as much better. You notice that the face, let me go ahead and forgot. Change this to red. I like red. Okay, so now the frequency used to cross over at 7 kilohertz. So now it's crossing at about 16 or 17 kilohertz, while the relay was crossing at 20, and the phase is around 46. about 46 degrees. Okay. Well, there really was 60. So it's a much better improvement. Okay. As a matter of fact, I think I already have that copied. Okay. So this plot is with a constant voltage signal, FRA signal. Let's go ahead and do that. And then this signal is with a variable amplitude signal. So you get a much cleaner. So basically at these lower frequencies I pump the amplitude high, and then as I approach the crossover I decrease the amplitude. That way I would cause less distortion or errors, and I got a much better plot. Okay, so now one of the things that you can do also is, I won't run it, but if you want to do the plot of your output filter, then you would set the measurement from out to EA. So then all you would have to do is come here, go to the FRA and say out to EA, and then press run. Okay, and your plot should look like this. So here is the frequency response, and this is what you would expect from the output filter. Basically it's a low pass filter. You have a pole here, and once you have the pole, then you have a 0 here, and this is exactly what you would expect. So you can take this type of measurement using a switching model. Okay, so we're not done. So now let's say you want to get the frequency response of your error app. That's easy. Then you want to plot from EA to in. So now all you have to do is go to the transient analysis setup, and now you would put the output or this positive node as EA, and then set this to in. And that's it, and then you press start, and you should get a Bodhi plot of your error app. In this case, this is the response, and if you notice here, this is the integrator cap, and then there's a little of an upward deflection going up. Okay, so that means that you have a 0 here, and if you look at your phase, anytime you have a 0 you have a positive deflection, and when you have a pole you have a negative deflection. Okay, so right here you have a positive deflection, and then right here you can barely tell there's a little of a negative deflection. So this is a pole. And how can you tell? Again, you look at the phase. The phase is going down. So that's a 0, and that's a pole. And this is what you would expect from an error app. So basically, now having a switching model, and by using this feature, you can get a loop response, the plant response, and your response from your error app. Okay, so this is a very nice feature to have. I think it's very intuitive. I think it's easy to set up. There's no scripts that you have to copy. You basically label your injection point, and you're able to let it run. Now, like I said, this is a feature that Pensar Development implemented. I've asked, actually, I requested them if they could put this feature. They've been working on it for several months. and they've been making improvements with some of my feedback. And the last feedback that I had given them was that I wanted to see if they could put the variable amplitude, and they managed to implement that this week, and I'm very happy about that, because now the simulator, I feel, is very, very good. You're able to use the FRA to extract these uh, uh, these Bodie plots, and you should be able to use this on either linear circuits or switching circuits. And if you have a, let's say, a topology that you're not familiar, then you should be able to at least print or get some useful information to at least verify your design. Anyway, some other information is, if you're interested on TopSPICE, and I want to remind everybody, I'm not connected with them. I'm a happy customer. I've been a customer for over 20 years, and I like the company because they've always been very receptive to requests. So anytime I requested, can you add a model, they've been really good about adding models. And if I thought or think of an idea as far as features, they've always been real receptive about taking care of the customer. So that's why I'm a user, and I try to promote it as much as possible, because I think it's a good value for your money. To have this type of feature, the only other simulators that I know that does it is PSIM, Simplex. Those are very, very fast, much faster than TopSPICE or LT. However, they're not SPICE simulators. Okay, so you can't import SPICE models that manufacturers have built, or import them, or at least that I know of, and simulate them. LT, you're able to do this type of simulation. However, LT has been bought by advanced devices, analog devices, and how much longer or they will support it, I'm not sure. And my understanding is I haven't seen real improvements or addition of features into LT for a long time. My understanding is that people have asked for improvements or features, and they're very reluctant to change it. As far as pens are, they're very good at implementing features or requests by customers. So that's why I'm very, very a fervent user of TopSPICE. Anyway, if one other information is, if you do want to get a copy, if you mention my name, Robert Bolaños, as a referral, you can get a 10% discount off of the list price. And if you are a university student, if you use my name, Robert Bolaños, as a referral, provided that you can show that you're a student, as long as you show some kind of that you're enrolled in a class, and that you're going to be using SPICE, then you get a 50% discount. So those are nice discounts that people can get. I hope that you take a look at it and see if it's something that you can use. Anyway, if you have any comments, you can then send them to me at rbola35618@aol.com, or you can post them on this channel. Any other comments or requests for SPICE, you can send them there as well. Again, if you find the video informative, please subscribe, share, and give a thumbs up. Thank you very much.